So what we want to do now is we want to talk about if I have these double integrals, remember they're finding volume of a solid basically under over a specific region under a given curve. What happens if it might be really complicated to evaluate just using our Cartesian coordinates, meaning integrating this with respect to x and y? So we know we've graphed a lot of these functions in 3 dimensions. They can kind of get messy with bounds, especially if I have circular bounds. That would be really difficult to describe solely in terms of x and y. So the first coordinate system we're going to kind of work with is polar coordinates. So I'll refresh on just kind of switching stuff over, like our basic, what does x equal, what does y equal. But if you do need a refresher on polar coordinates, there's ample videos out there to just watch something to kind of just remember how to convert back and forth between these. Otherwise, this video would be way, way, way too long. So first, I want to just show you the benefit of why we're going to do this. So suppose we want to evaluate a double integral. So we have the double integral over the region R of some function integrated with respect to x and y, where R is one of the following regions. So for the first one, let's just look at the unit circle, because we know a lot of our shapes ended up having that in the xy plane. So let's suppose we got our circle here, make sure it looks decent, and then it goes out a distance of 1 in every direction. So this would be x squared plus y squared equals 1. And here is R. Okay. So I'll call this one R1. If I wanted to integrate this with respect to x and y, one of the bounds is easy because it's the constants that this changes between. So say if you set this up in the form dx dy. Your y then would change between -1 and 1. However, your x would have to start at the left half of the circle and go to the right half. Let's pick one that actually shows up. And in that case, what you'd have to do is you'd have to solve this equation for x, and you're going to get some really kind of nasty bounds. Because over here, this would be the left half of the circle. It would be negative square root of 1 minus y squared. And then this right half would be x equals the positive square root of 1 minus y squared. These would be just in your bounds, and that would be potentially disgusting when you then go to integrate with respect to y at the end. And even if you flip-flop this, if you did dy dx, not much really changes because of the symmetry of this. So if I do dy dx, then great, okay, my x is changing from -1 to +1. But the top half of the circle, if you went and solved for the y component, you would have to take a square root, and again, you get plus or minus. So the top half of the circle would be given by the positive square root of 1 minus x squared. And the bottom half of the circle is negative square root of 1 minus x squared. So absolutely atrocious bounds. Okay. To give you another example, let's say we have semicircles. And maybe we've got one semicircle here, which is x squared plus y squared equals 1, but just the top half. And then we've got the other semicircle of radius 2. Not perfect, but that's okay. So this would be x squared plus y squared equals 4. And maybe the region I'm integrating over is the area between these two. This, I couldn't even tell you how to set this up in terms of x and y. Okay? So this would be really difficult to do, and you'd probably have to break it down to like this section and this section. But even within there, it's pretty complicated because your x bounds, it depends on where you land in here. If I pick this x value, it goes up to this particular function. But then if I'm picking a value between -1 and 0, it's starting at one curve and going to the other. So you'd really have to break this down probably into 4 separate pieces, or maybe even 3 you could get away with. So this would be atrocious to have to go through. But because both of these are circles, it's much easier to describe in terms of polar coordinates because we know that just deals with a circular region. So here, both regions are difficult to describe in terms of x and y. However, they're easy to describe in polar coordinates. So if I think of region 1, remember for polar, you need 2 things. You need the radius and you need the angle. So here, if I'm talking about the unit circle, well, my radius is between 0 and 1. So it really gives constant bounds on r. And then same thing to get the whole circle, you need to go from 0 to 2 pi for the angle. So theta will be changed between those values. So if I can switch over to polar coordinates, I really get constant bounds for my 2 variables. And that's amazing to deal with instead of functions inside my bounds. And then likewise, if I go to describe region 2 in terms of r and theta, here, because it's trapped between 2 circles, well, your radius is then between 1 and 2. You start at the circle of radius 1 and end at the circle of radius 2. And then here, because it's a semicircle, your angle starts at 0 and goes to pi. So theta is trapped between those values. So again, I'm getting constant bounds instead of function bounds. Okay? So switching over to polar, we'll give easier bounds. But that's not the only thing that has to switch. Think of when you make a u sub, you've got to switch the inside component and you have to switch over that dx when we're in just calculus 1. Well, here I've got dA, the dx dy. So how do I switch that component over? You're going to see the inside changing the function isn't going to be a ton of work. It's that dA that will be a little bit difficult. So switching over will give us easier bounds, but now we need to figure out how can we change everything else. Okay. So that is what we're going to spend the next probably 15 or so minutes on. We want to see how does this dA end up switching over. And so again, I'm going to break it down just by working with smaller components, see what it looks like on that particular region, and then we'll go ahead and see how it would generalize in that limit. So our goal is we want to find the volume of the solid under the surface z, which is a function of xy, above the region R. And again, this region R is very likely to be described easier in polar coordinates. So just to give you a visual, let's go ahead and do the back X and Y, and I'll change those to dotted in a second. So this we want dotted, and then this one we want dotted as well. So maybe our region R is a circle. And a circle can easily be described in polar coordinates. And so I have some function, maybe it's way up here, and it does something funky, I don't know. Looks like this. Okay. What I'm trying to figure out is what is the volume underneath this surface above this region R. So basically, what does this solid end up having as a volume? So we could connect down those sides. Okay. So again, the region R will be easy to describe in terms of polar coordinates. If I've got this function, this is what's going to go inside my integral. So I'd have to switch over the x and y. And if you remember our x, we can switch over using r cosine of theta. Your y, you can switch over using r sine theta. Okay. So inside our integral, all of the x and y's for this function, we're just going to replace by r cosine or r sine theta. You also, if you have this relationship x squared plus y squared, remember that equals the radius squared. And then the last conversion we had was tangent of theta is y over x. This one won't really appear too frequently for us though. Okay. So now I can switch the bounds using r. I can switch the inside of the integral. What now happens to that dA? What is that change in area? So I want to show you where this comes from because it's really going to bring us back to our trig days and even maybe your geometry days from high school when you went through area of a sector. So this is our goal. What happens to dA now, which is dy dx or dx dy, either one. So let's go ahead and consider the polar rectangle. Basically meaning your r has constant bounds and your theta has constant bounds. So this is all the values of r and theta, where your r is trapped between two values, a and b, and your angle is trapped between two constants. And since our angle is Greek, we're going to use alpha and beta to describe this. Okay. And then I'm going to assume a couple different things. I want b to be the bigger of the radii. We don't want to deal with negative radius here and shooting through the pole and all of that. So a is going to be the smaller value than b. And then the other thing I want is that beta is going to be the bigger angle. And the other thing is it's got to be less than 2 pi. Because if it's more than 2 pi, that means you've gone around that circle multiple times. And you don't want to double find that volume. Okay, so I want something specific between 0 and 2 pi. So what ends up happening, we're going to draw a little picture to try to dissect this. And move this over here. So this is our x, this is our y, and remember we can always put that polar plane just directly on top of this. Our radii is switching between two values a and b. And so if you think about r equaling a, that gives you a semicircle or a piece of a circle. R equals b is also corresponding to a circle. Okay. Not the prettiest, but that's okay. So here's r equals b, r equals a. Then theta equaling the first angle alpha corresponds to a ray. And then beta is a bigger angle, corresponds to another ray over here. Okay. So this is why it's called a polar rectangle, because it's not really a rectangle. It's giving you a piece of a circle. Right? So what we're trying to do is we're basically splitting our region R into a grid like this. I want to approximate the area on this region, and this is going to help figure out how my change in area is going to occur. Because before, what we did in the XY plane was we built a grid that was just parallel to our X and Y axes. But now what I'm doing is I'm building a grid on the polar plane. So instead of it being rigid lines like that, it's giving me semicircles and then giving me rays. So really what's happening is I'm dicing up my theta into equal pieces. Okay. And so each one of these is the change in the angle. And then I'm doing the same thing to R. I'm breaking that down into smaller regions of equal length. Okay. And in that case, it's giving me semicircle pieces or arcs of circles. Okay. So this is how we're forming that grid. And I'm going to take a deeper dive into one of these, which is some random piece on here. So we're going to see, what does this look like? Okay. So we've got delta R, and then we've got delta theta, and then we have delta R here. Okay. So I'm going to do my best to draw this nicely, but what we've got going on is this slice. Okay. This is the smaller of the theta values. This is the bigger of the theta values. And the difference between them is exactly what we're calling delta theta. Okay, we've split that into those equal pieces. Okay, and then likewise, we have our grid going in this direction, which is the arcs of those circles. And these deal with my change in R values. So now we use the subscript I. That's the bigger R, and this is the one right before it. Okay. So delta theta is the difference between these two angles, and it's actually the angle that forms these two rays together. So then delta R is what we're going to call this. That is the difference in the two radii. Okay. So remember, dx dy, that just came from the change in x, the change in y on that grid. So same thing here, my delta A is going to deal with the change in R and the change in theta. It's just I'm not using a rectangle. These are actually areas of sectors because we've got these curved arcs for these edges and then these angle that's formed between them. So this is exactly my change in area on that specific grid. Okay. So if you remember the formula for an area of a sector, fantastic. If not, I'm going to refresh you on it because I doubt you do. So recall the area of a sector is A. It's 1/2 times the radius squared times the angle. So for us, what we really have, use a different highlighter, we have the area of this bigger sector formed by Ri and still that angle, delta theta. And then I need to remove the area of the smaller sector, which deals with the radius Ri minus 1. And if I take the difference between those two, it gives me exactly this region, which is the change in my area on that portion of the grid. Okay. So delta A is going to be 1/2 Ri squared times delta theta minus 1/2 Ri minus 1 squared delta theta. All that is it's the area of the bigger sector minus the area of the smaller one. And what I want to get is I want to see, we've got delta theta, but how does delta R come in? Because remember, delta theta is going to turn into the d theta. So I want to figure out, where does delta R come from? So all I need to do is manipulate this a little bit. I'll pull the 1/2 out, and then we've got the bigger radius squared minus the smaller radius squared. And then we're also going to pull the delta theta out. Okay. Then this in here is something squared minus something squared. That factors really nicely. So this is 1/2 the bigger radii plus the smaller times the bigger radii minus the smaller, which is fantastic for us because this is exactly what we're calling delta R, the change in the radii. And then here what I'm going to do is I'm just going to move that constant into the bottom here. Okay. And so if you remember when we were going through and we were figuring out which endpoint to evaluate it at in Calc 1, it didn't matter. You could pick a point that was in the middle too, somewhere randomly. Even when we started with just dx dy, you could pick any point on that grid to evaluate the function at. We just picked like the upper left corner, the upper right corner. But once you let the number of subintervals go to infinity, the point itself was insignificant. That's exactly what this is. Okay? So if you think of it, it's the average of the radii. So what you'd be doing is you'd be using this point here for your radii to plug into your function. But again, in the end, that does not matter when you're taking that limit. Okay? So what we're going to do is we're going to call that Ri bar. It is the average of the two radii. So we are finally almost there. We're going to let Ri bar be the average of these two radii. Delta R is the difference in the radii on the grid. And delta theta is the difference in the two angles on the grid. Then that means our change in the area on the grid is given by the average of the two radii, delta R, delta theta. Okay? So ultimately, since x can be replaced by r cosine of theta and y can be replaced by r sine theta, we have the volume of the solid is given by the double integral over the region R of our function dA. Well, breaking that down into its limit definition, this was the limit as m and n go to infinity of that double sum of our function evaluated at the x value and the y value and then delta A. Your I goes from 1 to M. Your J goes from 1 to N. And then realistically, you can say these are those right endpoints or that upper corner on the grid. But likewise, I could also say these are the midpoint values. Okay? It does not matter the point it's evaluated at. So now we can switch everything over in terms of polar in this limit. Now we can still use M and N. That doesn't matter. We still have a double sum because in here the x is going to be replaced by r cosine of theta. And then again, we can say these are the midpoints. It doesn't matter. And then same thing in the y component. The y is replaced by r sine theta. And we can say it's the midpoint of each of those values. Now, this delta A, however, in terms of r and theta, becomes the midpoint times delta r delta theta. Okay. So when you take this limit as both m and n go to infinity, it turns into a double integral. The f gets evaluated at r cosine theta, r sine theta. Okay. The theta is going to change between alpha and beta, so we'll make that the outer values. And then our r, in this case, has these constant bounds a and b. The only difference now is this. In the limit, this will turn to just r, and then delta r turns to dr, delta theta turns into d theta. So the hardest thing you have to remember is when you switch over to polar coordinates, you're going to add this extra r that comes in from the dA. So this is why I've made a huge emphasis on making sure you write that d whatever at the end, because for us, it's going to introduce new functions. And if you're forgetting these extra functions at the end because you didn't write that dA, dx, dy, it might make your integral impossible to do. Okay? So be very conscientious. This is a proper way to write an integral. If you're leaving it off at this point, it's not a good thing. So what I want to start with is we're going to find a volume of a solid over a specific region. The one thing I do want you to get into the practice of, though, is still set these up in terms of x and y. It is going to be important for you to be able to write it in every different form that we have. And then we'll go over and we'll see switching is going to make a lot more sense here. So from there, then we'll evaluate this using polar coordinates. And then we'll also show what the volume of a cylinder is. We'll prove that. So let's do our first example. Let's find the volume of the solid. Enclosed by the curve z equals 5, z equals 2 minus y, and x squared plus y squared equals 4. So you can see I've got a circle right there. It's going to make sense that polar coordinate is going to work for us. Okay. Now the problem is with this one, it also doesn't explicitly tell me my region R. It just says enclosed by all of these curves. So what I need to do is I need to graph all three of these and see what this solid looks like. So this is why graphing is also very important for us. So I'm going to take my time to draw a really nice picture as to what's going on here. And we'll go out in each of these directions as well. So we've got a circle of radius 2, x squared plus y squared equals 4. And then technically, because there's no z, this actually forms a cylinder. So that would be a circle of radius 2, and then it would continue up forever. Okay. So I'm going to worry about graphing this one last. Instead, what I'm going to do is focus on these two, and I know that it's going to intersect this cylinder. So basically, the cylinder is going to slice through both of them. Okay. So let's start with this plane, z equals 2 minus y. X is free, so it can be absolutely anything that it wants. If I were to think about just graphing that line, well, when y equals 0, my z is going to equal 2. And I'm actually going to draw up 5 in this direction because we know we have the plane z equals 5. So when I plug in y equals 0, my z is going to equal 2. When y equals 2, z is going to be 2 minus 2, so my z is 0. And then if I plug in negative 2 for y because I need to hit the edge of that cylinder, well then my z is going to equal positive 4, which is up here. So the plane is going to contain this line. And again, realistically, what would happen is this would continue forever in these directions. However, I do not want to draw this whole plane because, again, I'm going to take this cylinder and it's going to slice through it. So really what's happening is it's going to get sliced kind of like this. Because it's got to fit inside the cylinder. So this will be z equals 2 minus y. And then same thing, z equals 5 is going to be a plane up here. The x and y are completely free, so it's parallel to the xy plane. Z just has to equal 5. But again, I'm taking this cylinder and I'm going to slice right through that thing, and it's basically like a cutout cookie. You're just going to have a circle up here. Okay. And now I can fill in my cylinder. It just goes straight up and down. So this is x squared plus y squared equals 4. Okay. So this is the volume of the solid that I want to find. Okay. So before I get into finding the bounds, we have to figure out what the inside function is. It is a double integral over some region R. We'll figure that out in a minute. What I need here is I basically need the height of my function. So what's happening to find this particular volume, because you have this gap missing underneath because it's sandwiched in between these two, it's just like we did in Calc 1 when you're finding the area between two curves and finding the volume between these two solids. So I'm really just going to take this top function and subtract the bottom function. So the inside is going to be the top minus the bottom. Okay. Now what I need to figure out is what is this region of integration? Well, in this case, you're only going out as far as that circle. So really what's happening in the xy plane is the circle of radius 2 is dictating everything because the cylinder sliced through both of those planes. So this is my region R. So if we zoom in on the xy plane so I can figure out all of these bounds, we're never going to leave this circle of radius 2. here is r. So we have the curve x squared plus y squared equals 4 to dictate what's going on. So I'm going to set this up first in terms of rectangular coordinates. The inside just becomes 3 plus y when you subtract the 2, which is not too bad. And then let's go ahead and set this up as dy dx. Because of the symmetry, it does not matter what you do. So for the outermost bound, that's the constants that x changes between. So the outermost bound is -2 to +2. Now what I need for y is I need to figure out if I pick any x value, say right here, you're starting down at the bottom half of the circle and you're going up to the top half. Starting at the bottom half of the circle, going to the top half. Okay. So if you were to rearrange this, that's y squared is 4 minus x squared. Taking a square root gives you plus or minus. The bottom half of the circle is negative square root of 4 minus x squared. And the top is positive square root 4 minus x squared. So these would be the bounds with respect to x and y. So although the inside function is not hard to integrate, when I go to plug in these bounds, it's going to make a complicated integral, and I don't want to do that. So instead, since I have this circular region, let's switch over to polar. So on the inside, we're going to switch x by r cosine theta. We switch r, or y, by r sine theta. I don't have x squared or y squared, so that's not a problem here. And then the other thing I need to do is I need to remember when I switch over dA, it's going to introduce an extra r value. Okay. So I'm going to worry about the bounds in a second. 3 doesn't change, but y gets replaced by r sine theta. And then the dy dx becomes r dr d theta. Okay. Now I can go through and I can find my bounds. So starting with r, which is that first integral, because I'm dealing with a circle of radius 2, my r changes between 0 and 2. And then when I go to switch theta over, to get this full circle, I've got to go 1 revolution. So that would mean that this outer integral has the bounds 0 to 2 pi. So really nice again, because now I have constant bounds, which is way easier to work with. So from here, we can actually evaluate this integral. But I do need to distribute that r out. That's 3r plus r squared sine theta dr d theta. So integrating with respect to r first, because I can't separate these, becomes 3/2 r squared plus 1/3 r cubed sine of theta, evaluated from 0 to 2. And again, we're evaluating r to begin with. Thankfully, when I plug in 0, everything is going to cancel, so I really just need to worry about plugging in 2. So when I plug in 2, r squared will be 4, divided by 2 gives me 2, so this will become 6. And then 2 cubed is 8. So it's 6 plus 8/3 sine of theta. And then just so I don't have to keep scrolling. I got plenty of room over here. Let's finish the integral on this side. I now just integrate with respect to theta. So that becomes 6 theta. Antiderivative of sine is negative cosine. So that's minus 8/3 cosine of theta. And evaluated from 0 to 2 pi. So plugging in 2 pi gives us 12 pi. Cosine of 2 pi is going to be 1. So it's 2 pi minus 8/3. Plugging in 0 gives us 0. And then cosine of 0 is positive 1. So it's 0 minus 8/3. Well, that's negative 8/3 plus 8/3. Those both end up canceling. And the volume of this solid is 12 pi. Okay. So you can go through, you can try this integral if you want to, but really the second you take your y derivative and plug in those bounds dealing with square roots, you're going to see this is not a way I want to go. So that circular region, huge indication that polar is going to be the best for us. Right. So let's do another example now, and we'll go ahead and we'll do this actually both ways. So we're going to find the volume of a cylinder. I'm going to prove it first using rectangular coordinates, and then I'm going to switch over and use polar coordinates, and you're going to see how beautiful this is in comparison. So unfortunately, usually when we have a cylinder, we have a height h and then we have a radius r. I just don't want to use r because that's what we're calling in polar coordinates. So we're going to work with a circle of radius a. So we are going to prove that the volume of a cylinder with radius a, which is a constant and positive, and height h, which is also a constant and positive, is, if you remember, its area of the base, which is pi r squared. So in this case, pi a squared times the height. Okay. So I want to set this up using a double integral, and we're going to have to figure out what the inside function is and what our bounds are. So I'm going to draw a little picture first, because we know how to graph a cylinder. I'm going to go ahead and draw the backs of these as well. So we've got a circle of radius a down here in the xy plane. So this would be given by x squared plus y squared is the radius squared. So this is a, negative a, negative a. This is what's going on in the xy plane. And then our cylinder has height h, so let's say h is up here. And so we draw our sides of the cylinder up, and then the top of the cylinder here. Okay. So really the cutoff is the plane z equals h, that caps the top. And then in our x and y direction, we're just going out in this circle of radius a. So if I want to find the volume of this thing, it's the double integral over this region R. The inside function is just h. And then we go ahead and integrate with respect to x and y. Right? Now, what you also can do is a couple different things. Because this does have symmetry, you can instead just find the volume on one quadrant or one octant and then multiply it by 4. That's going to work a lot for us when we're just finding volumes of things. I'll show you how first you can set it up instead, though, using the whole XY plane that is going through. So we'll do a ton of different ways for this. So here is our XY plane zoomed in real nicely. We've got our circle of radius A, and this is the region R. So this is x squared plus y squared equals whatever this radius is squared. Okay. So let's do this. Again, the symmetry is really nice, so it doesn't matter. Let's set this one up as dx dy first. Okay. Well, in that case, then our y bounds is what y changes between. So here that would be negative a to positive a. So again, we can fill all of these in so you can see that. And then once you pick that y, your x value will start at the left half of the circle and it goes to the right. So this left half of the circle, if you were to solve for x, would be the negative square root of a squared minus y squared. That would be your lower bound. And then the upper bound is the right half of the circle, which is the positive square root of a squared minus y squared. And then if you wanted to do this in the other way, it would just be very similar, except these would be x's instead. So I'm going to omit doing that one. The other thing we can do, however, is we can find the volume just over quadrant 1. Okay? So using symmetry of the volume, we can find the volume in octant 1 and multiply by 4. That's a little bit nicer. So we'd have 4. We still have the same integral. Okay. And then here we'd have our y changes between 0 and a, because it's just in octant 1. And then our x is going to start at 0 and go to the right half of the circle. So it'll go from 0 to the square root of a squared minus y squared. Okay. So now this, we can go ahead and we can take an antiderivative of. So this gives us the integral from 0 to a. When I take the antiderivative of the inside, it just gives us x. And then we go from 0 to the square root of a squared minus y squared. And again, we're going to evaluate x at this. And then we go ahead and we integrate with respect to y. So plugging that in, we get from 0 to a, we get h times this expression, a squared minus y squared. And when you plug in 0, it does not matter. You just get dy. So unfortunately, this is not a pretty thing to have to take an integral of. Realistically, this is going to end up being a trig sub problem. And we really don't want to do trig sub if we don't have to. Okay? The other thing at this point when I'm evaluating this integral, y is just that dummy variable to tell me what I'm integrating with respect to. It does not make a difference. You can switch it over at this point and you could say, okay, this is x dx instead, and just replace both the y's by that. Doesn't matter. But what I need to do in order to integrate this is I have to get rid of the square root. I don't want that. So because I have the constant minus the variable, that tells me it looks a lot like 1 minus sine squared equaling cosine squared. So if I make a substitution involving sine, it's going to shrink this down and it's going to go ahead and get rid of my square root. So specifically, the substitution I want to make is because this is a squared, we're going to let y equal a sine theta. And by doing so, dy is going to be a cosine of theta d theta. Then at this point, I'm also going to go ahead and I'm going to change my bounds because I do not want to go back to my starting variable. So let's move this over a little bit. So beginning when y equals 0. To figure out my theta bounds, we go ahead and plug in y equals 0. So we get 0 equals a sine theta. A is just a constant, so this is the same thing as saying 0 sine theta. Well, that means theta is going to be 0. So my lower limit happens to stay. When y equals the upper bound a, this gives us a equals a sine theta. Dividing by a is the same thing as saying 1 is equal to sine theta. So when this happens, is it pi over 2? And then you can go ahead and you can plug everything in at this point and then figure out how it simplifies. I'm going to off to the side instead see how does the square root of a squared minus y squared condense. So if I plug this in for y, this is a squared minus a squared sine squared theta. They both have the a squared in common, so we factor that out. And then 1 minus sine squared is cosine squared. And at this point, technically, again, when you take a square root, you get an absolute value of the thing on the inside. But if you remember the restrictions we made long ago, what we would have to do here is we would pick that theta to be inside the interval negative pi over 2 to pi over 2. This way it took on all the values of sine. And when you do that, that's quadrant 1 and quadrant 4. So cosine is positive. And then a is the radius. It's also positive. So the inside is going to shrink, which is fantastic. So way back up here, I'm going to take one extra step and I'm going to pop out that h because it's the height, it's a constant. And then we can go ahead and we can switch all of these pieces over. So our bounds now for theta are 0 to pi over 2. The inside is the square root of a squared minus y squared. That just becomes a cosine of theta. And then we have the dy, which again is why your dy's are so important. That becomes a cosine of theta d theta. Okay. So a times a is a squared, and again that is a constant, so let's pop that out front as well. And then we're integrating from 0 to pi over 2 of just cosine squared of theta d theta. And if you remember one of your trig identities here, to integrate cosine squared, we'd have to use that it is 1/2 times 1 plus cosine of 2 theta. And now we can go ahead and integrate, and I can also pop that 1/2 out front and condense it with the 4. So this is 2a squared h. Then the antiderivative of 1 is going to be theta. Antiderivative of cosine of 2 theta is 1/2 sine of 2 theta. And then we evaluate this from 0 to pi over 2. So plugging in the upper bound will give us pi over 2. When you plug that in here, this will be sine of pi. So that will end up going to 0. Then when you subtract 0, it's 0 minus 1/2 sine of 0, which is 0. So really, all of these pieces disappear. That's 0, that's 0. You end up with 2a squared h times pi over 2. The 2's cancel, and you get exactly pi a squared h. So the volume is cylinder, which is area of the base, which is a circle, times the height. So a long amount of time to do this in rectangular coordinates, and it required trig sub, which we really don't want to do. Now let's go ahead and let's do this using polar coordinates instead. So I'm going to go back up here for some time, and I'm going to just copy my picture down. And then our region in the xy plane is that circle of radius A. All right. So in polar coordinates, we have the following. Again, the volume of this thing is a double integral over the region R of h dA. Well, we can switch this over to polar. H and the inside has nothing to do with x or y. And then dA becomes r dr d theta. Going through my r bounds, that's the circle of radius A. So the bounds on R are from 0 to A. We need to go around the full circle. So the theta bounds are 0 to 2 pi. So already looks way, 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 way cleaner. And this is actually a super nice integral because the h pops out. And then really this inside is separable. There's no theta. So what I can do is break this down into two separate integrals. So we've got the integral with r dr, and then the integral with just 1. Theta is changing between 0 and 2 pi, and then r is changing from 0 to a. So this first one, if we run through that, that's 1/2 r squared, evaluated from 0 to a. And I'll come back and do the second one next. This gives us 1/2 a squared minus 0. Then for this, the antiderivative is theta, evaluated from 0 to 2 pi. And really, that's just 2 pi. So rearranging this, the 1/2 and the 2 canceled, and you get exactly pi a squared h in all about 2 minutes as opposed to 15 with rectangular coordinates, right? So you can see the benefit of having all these different coordinate systems. Again, it just depends on the problem itself. One thing you will have to get accustomed to is if you're just given the integral and given the region, how do you figure out which system to use? And so if it's got something circular, it's a good idea that you're going to switch it to polar. When we move into triple integrals, that's just going to be cylindrical coordinates instead. So you're adding a third component to it. Okay. So I got one last example to try. And then that will be it for double integrals. We're going to find the volume of the solid. Under the surface, z equals xy, and above the region, on the xy plane, in octant 1, which is bounded by y equals x, y equals 0, y equals the square root of 4 minus x squared, and y equals the square root of 1 minus x squared. Let's make this y look a little bit nicer. And then let's get this to a new page so we don't have that line in the way. So hopefully at this point you recognize what these are. They're just semicircles, just the top halves because it's the positive. But again, if you need some extra help with that, again, just kind of manipulate this until you see what the equation is. When you take a square root, it's definitely greater than or equal to 0. So again, my y is greater than or equal to 0. Squaring both sides, we'll get rid of the radical, and then adding x over gives you a circle of radius 2. And likewise for this other one, because it's written in that square root form, you know your y is greater than or equal to 0. Square both sides and add x over to get a circle of radius 1. But it is just the top halves of these circles. Because your y is greater than or equal to 0, right? I don't want to graph this surface because I don't know how to do this, but all I know is it's just underneath that. So this is going to be the thing that goes inside my integral. The rest of this is just dictating the bounds in the xy region. So it's giving us that region R we're integrating over. So I want to go ahead and I want to graph this to get a good picture of what's going on. They tell us it's an octant 1, so I really just need to draw quadrant 1. And we know that we're dealing with circles of radius 1 and radius 2. So try to draw them as cleanly as possible. So we've got our circle of radius 1. That will be y equals the square root of 1 minus x squared. And then we've got the circle of radius 2, and again, it's just the top half, which is 4 minus x squared. We've got the line y equals x, which we know bisects this right in half. And then we've got y equals 0, which is just the x-axis. So our region R is right here. Definitely do not want to do this in rectangular coordinates. I don't even know how to set this up nicely in rectangular because you don't have constant bounds really for either of the variables because this goes a little bit over and I don't know what this y value ending at is. I've got way too much stuff going on here. So this one I'm not going to be able to set up in rectangular coordinates. However, I am searching for the volume over this region under the surface xy. Okay. So now we can switch everything over to polar because that's going to make way more sense here. So I'll start by switching the inside and then come back to the bounds. X is r cosine of theta, y is r sine theta, and then dA, remember, introduces another r, so r dr d theta. Okay. Now for the bounds, when I start with r, the radii is changing between 1 and 2. And then moving on to theta, theta is starting at 0 and it's going to end at this ray y equals x, which because it bisects it in half, this gives us theta's pi over 4. So my bounds on theta go from 0 to pi over 4. Okay. So we can go ahead and now integrate this. I'm going to clean up the inside a little bit before I try to do so because I got too many r's all over the place. I have r, so we really have r cubed. And then we have cosine of theta times sine of theta. And then the beauty of this, again, I've got constant bounds. So what I can do is I can break this into two separate integrals. So we've really got the integral from 0 to pi over 4 of cosine of theta, sine of theta, d theta. And then we've got the integral from 1 to 2 of r cubed dr. Second one, hopefully straightforward. It's just reversing power rule. The first one, however, if you can't see what this is, let's not worry about the bounds. This is just a u sub problem. You can let your u be either one of these. I'll let it be sine though, because then du is positive cosine. If it did u equals cosine, then du would be negative, and now I don't have to worry about that. So this is really just integrating u du, which is 1/2 u squared plus c, which is 1/2 sine squared of theta plus c. So I don't need to worry about the plus c though because I've got bounds. So for this front piece, this will be 1/2 sine squared of theta, evaluated from 0 to pi over 4. And then I'll keep going through with this one and then figure out r. This will be 1/2. If you plug in pi over 4, it's root 2 over 2. So when you square it, the root 2 becomes 2, and then 2 in the bottom becomes 4. When you plug in 0, luckily, it is 0. So that really just gives you 1/4. Okay. Then for this second integral, not forgetting to go back, that becomes 1/4 r to the 4th, evaluated from 1 to 2. So that's 1/4, 2 to the 4th is 16. And then minus 1 to the 4th, which is 1. So this is 1/4 times 15 over 4. If you left it like that, not a problem, but those do simplify. You just multiply those denominators. And the volume of this solid ends up equaling 15 over 6. So again, we're going to extend to 3 dimensions or triple integrals. So now you're integrating with respect to x, y, and z. And polar and cylindrical are really similar to each other. It's just you have that z component as well.